It wouldn't be an exaggeration to say that all of calculus is based on the idea of what we call a limit. Derivatives, which we're going to spend most of this class talking about, are defined as the limit of a function. Integrals, which make up the other side of calculus, that we're going to touch on briefly here, and this talked about in more detail in the second semester, are the limit of a sum, or what's called a series. So before we start getting into technical details, we're going to take a look at limits from a high level so you can get a general idea of what we're talking about. And then we'll look at a specific example that we'll talk about it in more technical detail later in the class. All right, so I've got, excuse me, 3 examples for us to look at here. Right, the function on the left is what we refer to as well-behaved. Right, that's a phrase that we use to describe functions that don't do anything unusual. In this case, it's one that doesn't have any gaps or holes or asymptotes or areas where it's undefined. It's just a straightforward linear function. Now, for functions like this, the limit of the function as x approaches a point, say x equals 0, is just equal to the value of the function at that point. Now, things get more interesting with functions like this one in the middle that have a hole in them. One way to think about the limit, right, that's used a lot by professors, is to look at the value of the function at points close to 0. For example, f of 0.1 is 1.2. F of 0.01 is 1.02. F of 0.01, right, we'll look at one more here, is 1.002. Then we ask, what is this sequence of function values, of y values, getting close to? And hope that the students will see that this is approaching 1. Now, I'll admit, I've used this analogy for years, and it's not uncommon for students to struggle with it. They don't really have an idea, an intuitive feeling for what it means for a sequence, which is what we're looking at here, to approach a value. Right? If that's clear to you, then great. Now, another way to think of this that I think is a little more intuitive is to ask yourself, how can we fix the function? How can we make it into one that's well behaved? Right, now this function would be the same as the nice function on the left if we just filled in this hole. Right, and the y coordinate of the point that fills in that gap is what we call the limit of the function. Right, now, this value might not always exist. Right, with the function on the right, for example, there is no single point that we can add that makes the graph into one smooth, uninterrupted line. So in this case, we would say that the limit doesn't exist. All right, now so far, right, all of this talk of close to and approaches and well behaved has been pretty vague and non-technical. Now there are more technical definitions of the limit that make all of this precise, and that we'll get into as the course goes along. Now that you've got an idea of what a limit is, right, I want to show you how we can use this to answer a practical question. Right, so suppose we want to find the slope of the tangent line to the graph on the left at x equals 0. Now at first glance, that's going to be a problem, right? Because I only know the coordinates of one point here, right? And the slope formula requires 2, right? So, all right, what can I do? Well, one thing I can do here is I can find the slope of the secant line through that point and another point on the graph. All right, now visually, as the x coordinate of this second point here gets closer to 0, this secant line keeps dropping down, right, further and further here. And every time I do this, it gets closer to the tangent line, right? So we can reasonably expect that their slopes are also going to be close together, right? Now let's look at that secant slope in more detail, right? It's going to be the difference of the y values. That's 0 minus f of x divided by the difference of the x values. That's 0 minus x. So this point, let me label it here. This point is x comma f of x. All right, so let's see. F of x is just 2x squared plus x. All right, so if we substitute that into the formula, it becomes 0 minus 2x squared plus x over 0 minus x. Right? And I'm just going to keep doing the algebra and simplifying this. This is negative 2x squared minus x over minus x. And I can factor a minus x out of the top. Right? And this is minus x times 2x plus 1 over minus x. And then these cancel, and I'm left with 2x plus 1. Sort of. Right, sort of. There's a fine point here that often gets glossed over in algebra classes. These functions aren't actually equal to each other, because the first one, this one here, and every one above it, isn't defined at x equals 0. So it's only correct to say that this one is equal to the previous one, except when x equals 0. Okay, now to answer my question about the slope of the tangent line, what I really want to do is evaluate this secant formula at x equals 0, but I can't because it isn't defined there. Right, now, here's why I wanted to keep this graph on the right around. Right, this is the graph of y equals 2x plus 1 with a hole in it at x equals 0. This is the graph we were looking at on the previous slide. Right, so while I can't talk about the value of this function at x equals 0 because it isn't defined there, what I can do is I can talk about the limit of the function there. Doing that is going to be the key to answering this question and a lot of related ones. So at this point, hopefully, you've got an idea of what the limit of a function is, and at least a first impression of one of the things that we can do with these limits. Right, so in the next lecture, we're really going to start getting into the body of the class, and we're going to start looking at ways to make those ideas of closer and closer and well-behaved into something that's more mathematically precise.